Okay, anyway, so I just want to review a little bit of last time. Last time we talked about flat potentials, and of course that's when the Schrodinger equation has no potential energy. It's literally the easiest problem to solve. When a mathematician says solve this, they just mean solve the differential equation. What that means is they're looking for the wave function. They're done at that point. That is solved to a mathematician. And this is what you can get. Now I showed last time how the solutions are e to the ikx, e to the minus ikx, and I showed you how a mathematician would solve a double differential equation. Again, this is the easiest double differential equation that exists. And these are the solutions, but sine and cosine also work as well. And again, that's if there's no potential energy. Potential energies can have steps, though, and you can still work with this, so long as that the surface is ultimately flat, which is what we're talking about today. Anyway, all right, so that's what we talked about last time, but what I wanted to do is put it in context. This is something, we're still in undergrad land, and we also will be still this week, and then the next week, we'll get into a bit, then the bar is going to get raised. Sometimes I feel like maybe I'm going a little too slow, but whatever. UIC actually does teach about 2 weeks longer than most universities, by the way. Most universities only do 13 weeks, and so for undergrads who generally don't have a lot of money, this is very good. They're getting more instruction for the same price, so I appreciate that. Okay, so remember, one of the ideas of quantum mechanics is that you have to, we think of the wave functions of the Hamiltonian as being real, as being more important, so I have my more generic wave function here of an operator, and to ask questions of that operator, ask questions of that wave function, like what's your momentum, what's your angular momentum, whatever. You have to operate on it and get a number times the wave function. Unlike classical mechanics, where just taking the derivative of it is fine, that gives you velocity, and quantum mechanics says no, it has to be an eigenfunction, the function has to come back, so awesome. The hard part about quantum mechanics is while I've got these wave functions for the Hamiltonian, and you think of these as being very special, this may or may not work for another operator, such as momentum. Example, now all of these guys work for the Hamiltonian. If you do, I won't actually solve it, but if you do h e to the ikx, what you're going to get is h bar squared k squared over 2m e to the ikx. So that's a pass. So, oops, I gotta remember the camera. Camera doesn't take, I gotta write a little bit bigger. Okay, so that's a pass, and now I know what the energy is. But if I do momentum, I'm also fine on this one, and that's minus IH bar. And you can actually figure this out by simply taking the square root. Again, sorry, my handwriting is still bad. It'll improve. IH bar ddx of e to the ikx. Okay, so this guy is good. What you end up with is h bar k e to the ikx. Okay, so that's also a pass. So I know the energy and I know its momentum, and that's how I also know that that's that's a particle that's moving to the right. That's its wave function, and it has a positive momentum. So that has to be moving to the right. And a left wave would have a negative momentum. Okay, I just want to point out, if you did cosine here for the Hamiltonian, you get the same answer. Okay, but if you do this, you got yourself a problem. Uh-oh. What you end up with is what we'll get IH bar K sine KX, which is a big no. Okay, so again, part of the biz-knockerness of quantum mechanics is when you're asking questions of wave functions and it doesn't work. And then, lots of things could be happening. Maybe you haven't solved it right, maybe there's an uncertainty principle, or maybe you just need to use the expectation value. Okay, this always bothered me. I'm only bringing this up, I'll never bring it up again. This bothered me as an undergrad when I saw this derivation, right? So we can ask questions this way or we can ask questions this way. I notice that the answer is a bit more clean, right? So the wave function's gone. And here's the proof, and again, you see this in every textbook. Okay, here's what killed me when I was an undergrad. Why not stop here? Why are we going further there's your answer, it's there. If I'm going to then take, it's a number, it can go outside the integral, which is always true, that doesn't matter quantum mechanics or not. Once that number comes out the integral, I've just got a normalized wave function integrated, which is 1, and so now I've got my eigenvalue. But I had it here. What the heck? I mean, that doesn't, what the heck is up with that, right? The answer is that when you're trying to do cosine, you need to do it this way. So for psi is cosine, and you're trying to get the momentum, you need to do it this way. And what you end up with is, cosine kx, the complex conjugate of cosine is still cosine. Okay, then you get the operator minus I h bar dx of cosine kx. And then this ends up being cos times sine, which just goes to 0. Okay, so the average momentum is 0 if the wave function is a cosine, which is correct. Okay, so anyway, the answer to why this works, and this is in my silly textbook, so notice that I can use expectation value when the eigenvalue equation fails. And so that's why most textbooks they actually will not even show eigenvalue equations, they actually just show this. This always works, especially in a tough case like when you've got a cosine. Now, ultimately though, the reason that this works, and this I'm always fascinated with, is that cosine is actually a linear combination of the two things that are okay with momentum. So e to the ikx and e to the minus ikx are simultaneously okay with the Hamiltonian and momentum. Cosine appears to not be, but it's actually kind of false. It's what's hiding is the fact that cosine is actually composed of e to the ikx, e to the minus ikx. We know that these are okay with both operators, so cosine is too. It's just harder to see that. And any wackiness is resolved by doing expectation value. So again, I also want to point out, because this is one of the harder parts about quantum mechanics, is that when you have an operator, you have all kinds of wave functions that are its guy. Let's use more sophisticated terms. It's called a basis set. That are inside of its basis set. And again, those are its eigenfunctions. And then we got other operators that have their eigenfunctions. And the two, and remember I kept saying this is a Venn diagram, they may or may not overlap. And that is where quantum is really kind of a pain in the rear. If this didn't happen, and this often happens due to an uncertainty principle, all of this would be way easier. But anyway, so I'm just trying to review, and I'm just pointing out, just remind you some of the undergrad stuff about expectation values and whatnot. Since I got so stuck on that, and I never understood why as an undergrad, I kind of harp on that like kind of obsessively. Anyway, anyone have any questions from last time? Again, yeah, it's all still a little on the simple side. And so today are flat surfaces. Okay, so we're solving the Hamiltonian. And so again, the V is flat. I've been saying that the potential energy is 0. What you can do is you can have steps. And if you have a step in potential energy, it's no different than saying that the potential is 0, you just have less energy. So that's why I can use e to the ikx, e to the minus ikx for flat potentials, because even though it's actually bumping up and down, you can always call it 0 here or here just by saying you simply have less energy up here. And I'm going to write that down in a very formal way. I'm just pointing out the big picture. And so anyway, the potential energy can jump up and down, it can go to infinity. We'll usually set the bottom to 0 because why wouldn't we? Now the thing that gets funkalicious is when you have a very low energy wave, which would have a very large wavelength, and it hits a barrier, it's just going to decay exponentially. But something with a bit more kinetic energy, and a bit more kinetic energy would make it wavier. If it has more energy than the potential, it can cross that potential. Notice that its wavelength lowers a bit, but there it goes. And anyway, so that's the energies above the potential. And I'm going to solve this. Exactly. So here's the Schrodinger equation with potential energy. We're going to have just minus h bar squared over 2m, double derivative, and here's our wave function plus potential, which is not a function of x, it's just a number. And you don't really need to write that down, this is simple. So okay, so in the first case, when the energy is greater than the potential, the thing is that seems like, that's the one that I care about, because when would I ever be interested in something that has less energy than the potential? And anyway, I'll get to there in a second. What you do here is, actually you do this whether the energy is higher or lower than the potential. You just, because a potential energy is just a number, you just bring it over to the side. So again, stupid simple. And then what you can do is, this is exactly what we saw last time, using brute force mathematics for solving second order differential equations, where we see that there are two solutions. Since it's a second order equation, there's two solutions, and those are of course either the IKX, and we're not going to worry about normalization. And there could be some amplitudes. Usually it's called like A for the right wave, B for the left wave. We'll worry about that in a minute. I'm going to bring that up in a minute. I'm just going to leave it off for now. And K, to make it conform to our last lecture on solving differential equations. Again, there's not much to it. 2m e minus v over h bar squared. So if you pick one or both, whatever, let's just pick one, and plug that into the Schrodinger equation, plug that in here, you can see that what's going to spill out is going to be 2m over h bar squared e minus v. So this part times that is just going to be e minus v. So it works out, it's, like I say, it's undergrad simple. Okay, now, where it gets more interesting is if E is less than V. As much as you're thinking, like, when I look at this, I would always say, well, there's two cases, and I don't really, probably one of them I care about, one of them I don't. And I'd like to think that, what do I care about particles that don't have energies to get over barriers? This is actually the unusual case. This is not the case that you really are going to encounter in the lab, whether you're studying a nanomaterial or whatever. All right, for a nanomaterial, because that's my world, so I have to let me just start there. This is the kind of quantum mechanics when I am like when would I care about thinking this way? It would be when I have like a nanomaterial and I shine really high energy X-ray light on it. And what would happen is the electron, that'll be our particle, would shoot off of it, right? So the quantum dot's like a barrier. It holds the electron, but if I put enough energy into it, the electron will just pop right off. Okay, if I'm doing X-ray spectroscopy, cool. Then I need to think about this case. And I actually do X-ray spectroscopy, but that's not common in the lab, right? X-rays are kind of dangerous, and thanks to the atmosphere, we don't have a lot of X-rays just falling on our head. So my point to you is that this is kind of unusual. Okay, let me give you a molecular case. Actually, the same thing. Let's say that you're bio, you're bio, right? But you're bio, aren't you bio and organic?
Oh no, I'm with Jordan Smith actually. So.
I thought you were doing some biological work in that area.
Battery. It's on.
Oh, yeah, for some reason I thought there was a biological side to this. What about you?
That's me.
That's you. Okay,
Yeah.
okay. Now, I didn't confuse you, but anyway. Okay, let's say there's DNA. All right, so I mentioned an inorganic nanomaterial. Let's say it's DNA. Okay, DNA like UV light. If UV light hits it, it's same deal. The electron can just pop off. And if that happens, the DNA is damaged and you got cancer. Okay. So bad, but it's just not the normal case. This is actually the normal case. Energy less than V. And in that case, what you do is, if you look at this thing, if E is less than V, you got yourself a bit of a problem. You got a negative number. So let me just rearrange that. Let me call it K is now, so I'm coming from here to here, by the way, square root of, I'm going to put a minus sign in here, 2m V minus E. Okay. Energy is greater than, potential is greater than energy, so I like this. It's a bigger number minus a smaller number. Oh, but now I've got a negative sign. Uh-oh, what do I do with that? All right, so we're going to call that I kappa. Look out for that. In your textbook or any textbook, anything you find online, you have K for when energy is greater than V and a kappa for when it's less than V, and they just look the same. So I work really hard to make sure that my kappa and my K don't look the same. It's a bit of a pain. Okay, and of course, where kappa is square root of 2m. I just took out the minus sign, V minus E over h bar squared. So anyway, okay, in which case also you end up with the same, I'll just write it down. I should have written it down before, sorry about that. So if you look at what I did last time with getting the constants off to one side, so this conforms to what I did yesterday when I was showing you how you actually solve a second order differential equation. And of course the result ends up being, and now let me also introduce the idea of having constants inside of the deal, inside of the wave function. And of course the first thing, I'm usually writing e to the ikx, but now what I've got is I've got e to the I kappa x, and so two i's make a minus, so that e to the minus I kappa x. So now it's going the other way. Not really, and I'll explain that in a second. Kappa x. Okay. So what's happening is that this is a decaying exponential, but only if the wave is moving to the right. So that's what I drew here. So this is like the A wave decaying. Now notice that the B wave is increasing. Not really. This is for when the particle is moving to the left, right? So if your left is 0, x is a negative number that's increasing in magnitude, right? So this is right of 0 and it's decreasing, and this is for left of 0, which is also decreasing. This kind of messes with your head a little bit there.
So,
Any question?
in the kappa is the root of minus 2m, where's the minus come from?
So hold on. So this is correct.
Yeah.
E minus V is a negative number, by definition. Remember, these are two cases, right?
Yeah, but here
But I've got V minus E.
the E is less than V, right? So if you put negative,
Then I've got E minus V.
yeah.
What's your question?
Why you are putting the negative? You're balancing it?
Because they're the same. Because look, they're the same thing. This is K, this is K. They're the same thing.
Yeah.
So what's your question?
No.
They're the same thing.
Do we need that? Because E less than V, right?
Okay, this and this are exactly the same.
Yeah.
And you have to have this because this is what the Schrodinger equation is.
I'm asking why we need to change that.
All right, so now what happens is I take the minus sign out as an I, and then this guy is still E minus V. And what's nice is that this is positive. This is not imaginary anymore. So it's just friendly. And then I plug this into the general solution, e to the ikx. So in here, I shouldn't have done this. This was stupid of me. I I should have put, their constants here. Normalization. And anyway, so when k is now I kappa, you got a e to the minus, there's no imaginary component anymore. Right? So this is now just a decaying exponential, and that's also a decaying exponential, just don't forget you're going left. Yeah?
Yeah.
Right? Okay. Threw me out there, sorry. Yeah, you may be overthinking it. This is really brain stuff here. So, okay, now what do I want to say? Okay, so now the next thing is for your homework, and then I'm going to do 2 examples. And so I threw just a step barrier at you, which is a very classic example. And I asked you to get the reflection. If you have any trouble with that, if you want, you can Google that answer. There's really nothing to it. It's just a bunch of algebra. I'm going to do slightly different problems in class. So what do I want to do? Okay, so now one of the things that's a real biz-knocker about quantum mechanics is that, for this week, and I guess the next week as well, I'm going to be kind of following the traditional chemistry quantum way, which is I'm going to just introduce problems and then we'll solve them. Now again, in chemistry quantum, you just do that till the end of the semester, and hopefully you've seen so many examples it's in your head. After we're done with this flat potential stuff, I'm going to go in a different direction. I'm going to go in the physics direction, where you learn to do things by symbols, so the math is wiped out, so cool, and you can see more of the interior foundations of quantum mechanics, because you just don't have so many freaking integrals blowing your head off. It also gives you a lot more of a systematic way to solve these problems. Now, so that's why I'm doing that. Now, the chemistry way, when you have an example problem, people have been working, 100 years roughly on how to solve them, and they have clever ways of doing it. The problem I have with that is that it's very non-systematic. Every problem has a unique way of doing it, and what I kind of like routine. I like a flow chart. Okay, first do this, step 2, do that, step 3, do that, with that. Anyway, you don't have that with the chemistry way of teaching quantum. You have problems, solutions, and they're all really quite different, and you don't see a big picture from that. So I don't like that too much, and that's why I'm largely not going to do it. Okay, regardless, when it comes to the different problems you run into, and again on your homework you have the step potential, and you've got A plus B wave, turns into a C wave. This is the C wave. This is, so we have regions 2, region 1, and you have region 1, you got A e to the I kx plus B e to the minus I kx. Now you assume in region 2 that you just got just a decaying minus kappa, so you almost got myself kappa x. And all you do is you figure out the percent reflection is going to be the magnitude of the left wave divided by the magnitude of the right wave. Again, it's a fairly well-known problem. You should have seen that as an undergrad, and if not, it's very easy to solve. And you do that by boundary conditions. Now what I'm going to do, and I'm going to talk more about that in a second, is particle in a box. And so I'll center the box at 0. And traditionally we call the size of the box A, lowercase a. And so now I'm going to solve the wave function for this guy. And hopefully you know that it should look something like this. And that's basically a cosine. It's a cosine half-wave. And the next one is like this. So anyway, hopefully you know that, you remember it, or maybe it's kind of intuitive that it would look like that. Regardless, how do you solve these guys? And of course here, so that's your boundary for your homework. This guy, of course, is still This is a slightly easier problem, that's why I'm going to do it in class. We don't have any other region. We don't have any other region except the interior of the box, so we only have one type of wave function. There's nothing to the left and right because outside of the box the potential energy is infinite. So, okay, now, how do you solve the wave function? Again, how do you solve the wave function for this problem? Not that it's going to work necessarily for any other problem. God, that drives me nuts. But anyway, okay, what you do is in either case, in this case it's a little hard to see. So let me move to the right. I'm going to be a little generic. Is that you have to have boundary conditions. And then, in terms of solving for the wave functions, what does that even mean? That means you're solving the coefficients, by the way. Now the k here and here in both cases, these are square root of 2me over h bar squared. This guy is 2m v minus e over h bar squared. Anyway, all right, so by solve, what does it mean to solve? It means you find a, b, c, etc. And the way is to set boundary conditions. So in the first example, let's say that you're at x equals 0. You know that the wave function in region 1 needs to be equal to the wave function in region 2 at x equals 0. So that's because wave functions need to be continuous. Now here's a neat trick, and this is how you do your harder homework problem. You have another homework problem where you have a box in a box, and you have three. You have a boundary condition on left and right, and you got two more on the interior. So you've got technically four of these. Anyway, so you've got to be continuous, but you also have to be smooth. And to be smooth, you take the derivative, and those better be equal. Okay, now the trick here is you can actually kill two birds with one stone by dividing the two. Take the wave function divided by the derivative of the wave function. Actually, you know what? It's usually, actually is slightly easier. It just comes out practically easier to do the reverse. Sorry, I gotta look at my own notes. I'm kind of speaking off the top of my head. Divide the derivative by the value. Okay, so these are technically log derivatives. You set the log derivative equal to each other. It just ends up being, there's nothing like deep or meaningful about this, it's just practical. When you do this, it sets you up to solve the constants really, really, really quickly. And then that's really all there is. Once you have the constants, you have the wave functions, and with the wave functions now you get the energies. So remember there's also a flow to this. Somehow Schrodinger gave us the differential equation, so we have that. Solving it is done by the way I mentioned. And a mathematician's done, but as chemists, we then put the wave function back in the Schrodinger equation to get energy. So that's our flow of operation, especially for this chemistry part of quantum. Okay, so, okay, now again, this is how you do this guy, and it's also how you do that other problem I have where you have a box in the box. You would do that for every boundary condition. And here, let me actually point out for the homework, let me just help you out with that in case you haven't done it yet or you're having trouble. What happens is that this boundary condition, the boundary on the left and right being infinite potential, it dictates you whether you've got a sine or a cosine. And then your boundaries at A, plus and minus A and plus A, you use these at minus A and plus A. You use both of these, and you can solve for the coefficients, and then it gives you the energies. The boundary conditions at these other parts out here simply dictate whether you've got like a sine or a cosine in these regions, by the way. So anyway, just look out for that. Okay, then this guy's a little bit unusual because I do have a boundary. I've got minus a and a, but the boundary conditions, I don't have to line up with anything because there's nothing outside the box. So this is actually slightly unusual and is not necessarily helpful for your homework. So sorry about that. Here, let me know what. But it's a nice introduction. How do you think of quantum as a chemist, which again, I find suboptimal, but you do have to be able to speak to people outside of your department who maybe learned it entirely that way. Trust me, once you really get into Dirac notation, you're going to ask yourself, how in God's name does anyone do this without Dirac notation? And honestly, I don't know either. Okay, so we're particle in the box. Okay, so we're doing particle in the box. Okay, and what you got, of course, there's only one region, and K is as defined as before. Okay, but now your boundary conditions are the wave function has to be 0 at x equals a and minus a. Okay, and I'm kind of using some more mathematical symbology that you might see in the math textbook, or also like your Zachariah book. So anyway, but it's obvious what I mean there. So let's see here. Now what I do, again, this is what slays me about this stuff, is like, I'm going to just start doing things, and it's like, why the heck are you doing that? The answer is because it gives me the answer. Which makes me think that people, when they started deriving this stuff back in the late 20s and early 30s, I think they worked backward. I think they knew the solutions intuitively, and then they worked backward to show you like, oh, here's the easiest way to solve it. The problem is that when you see it forwardly, it's like, why are you doing that? And again, the answer is because it is the answer. Okay, so what I'm going to do is I'm going to write down the wave function at x equals a. Okay, that's e to the I kx, e to the I ka, sorry, plus b e to the minus I ka. Now what I'm going to do is I'm going to set it equal to the wave function at minus a. Notice that it's quite trivial. What you end up with is it's just you reverse your. Okay, so remember they're both equal to 0. Left and right, the wave functions are equal to 0. X equals a and minus a. So what I've done is I just set them equal to each other. And again, you might be like, well, okay, yes, 0 is equal to 0, but why? Okay, and the answer is algebra. So the next step is you might want to make a note. This is just pure algebra. There's nothing funky about this at all. So here's this, and then if I bring this over, I've got e to the minus I ka. Okay, now I've got this guy over here, e to the I ka, and I'm going to put a bracket around that, because if I bring this guy over, I've got e to the minus I ka. Okay, and there you go. These are the same, so they just divide out, and now you've got a is equal to b. And ta-da, that's it. That's literally it. To know exactly what a and b are, so what you can do is you can set them equal to 1, and then what you actually want to do is make sure that it's normalized, and then what you would find is that they're both equal to square root of 2 over L, over the length of the box. I'm not even going to worry about that. That's kind of not really all that important. Now here's a way that you want to kind of start thinking more at a graduate level. While, yes, I've got a is equal to b, so if a is equal to b, the thing is that you call this symmetric. Now, of course, if I had a is equal to minus b, I would have called that anti-symmetric. And just because, by definition, if you're thinking, well, what made me use those words? It's literally just because a equals b. I'm just going to call that symmetric, and then, of course, anti-symmetric is the opposite. Now, I also happen to know that e to the ikx plus e to the minus ikx, because they're the same sign, that's a cosine. If a was positive and b was negative, that would be a sine function, right? So remember that in my silly textbook, I have a little review of exponentials, and cosine is e to the ikx plus e to the minus ikx, and sine is e to the ikx minus e to the minus ikx. So anyway, so this is the symmetric solution. Okay, so again, I'm not going to worry about normalization constants. I'm not going to worry about normalization constants, which would be square root of 2 over the length of the box. So I guess that'd be 2 over 2a. Anyway, let me point out that if a is equal to b, and I'll just arbitrarily set it equal to 1, I'm going to look at the x equals a boundary condition. Oh, and then I want to remind myself what this is equal to cosine, 2 cosine, not that the 2 matters, Ka. Okay. Now what I've done is, now what I'm doing, by the way, is I've already, when I've done this, I've solved the wave function. I solved the wave function, but remember, I said in physics, you just stop there. Hey, you solved the wave function, I'm done, I don't care. In chemistry, we go further. Because what I'm trying to do is define K. Hint, I'm not trying to define K, I'm trying to define E. I'm trying to define the energy. Remember that once you solve the wave function, you want to go further and figure out what the energy is. Okay, so if cosine Ka is equal to 0, then that only happens when this has got to be equal to n pi over 2, where n is equal to 1, 3, 5, dot, 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 where n is odd. That already makes me notice something. That is like unsatisfying. Where's my 2's and 4's? Where's n equals 2 and 4? So I've already realized I've only got half the answers, by the way. I've not fully solved it. Regardless. Okay, so that's therefore. If Ka is equal to n pi over 2, therefore K is equal to n pi over 2a. Let me make sure I did that right. I think that's right. N pi over 2a, right. And that, of course, is equal to the square root of 2me over h bar squared. So now you have the energy. I'm not even going to solve it. It's right there. So anyway, here, I'll just remind you that the point is to solve for the energy. Okay. Now again, I know that I've only gotten half the solutions because I find it unsatisfying that I have a quantum number, so let's call that a quantum number. The quantum numbers, they just basically, there's all kinds of lofty descriptions of what quantum numbers are. The way I describe it is they keep track of what's what. They keep track of your ground state, which would be n equals 1, and your excited states. That's all that they really do. Unfortunately, there's multiple solutions, but to a mathematician, it's like, hey, look, there's multiple solutions. Whatever, I'm done. To a chemist, we recognize ground states and excited states. So it's much more meaningful. Remember, mathematicians just solve things for fun. Okay, so anyway, so now I've got the solutions. I've got the symmetric solutions. Sometimes your textbook may say, like, your textbook or any textbook will call them even solutions. But I know that there's an odd solution too. So what I've done is I've gotten this one, but now what about this one? That's a sine function. So where is my sine function? Here, I'll keep going down. I was going to go 2 more pages than I thought I would. Kind of need to speed up the pace again. I hope this is kind of stupid easy. Okay, where am I at? Okay, so where is my sine function? What I want to do is I want to check the derivative. Check the derivative. Now, wave functions are usually smooth and continuous. Now, I did continuous to solve for the symmetric wave functions. I said that they both, left and right, had to be 0. But what about the derivatives? Now notice that the derivatives on the ground state, they're not the same, left and right. They're not the same. That's a negative derivative and that's a positive derivative. Now this one, the sine functions, the odd functions, notice that they're, I intuitively know that this has to be here, yet I didn't find it. I intuitively know that I need to do continuous and smooth. And I've only done continuous, and look, I've only found half. I didn't find my sine functions. I didn't find my odd results. And the odd results, look at that. Rising slope, rising slope. These odd functions have equal derivatives at the edges. This one has equal wave functions. This is equal derivatives of the wave functions. So that's how I missed it. So if I check the derivative, what I've got is IK, I'm going to do the same trick. Let's see, here's the derivative, e to the IKX, but I'm at point A, minus IK B e to the IK minus IKA, because I'm at point A. And I'm going to set this equal to the derivative at minus A. So that's plus A over here. You might want to make a note in your notebook. Because like when I was reviewing my notes before class, I actually got completely confused what I was doing when I wrote these. I almost ran out of room. So again, this is plus A, that's minus A, and what I've done is I've said that the derivatives have to be equal. So I said the wave function had to be equal, now I'm doing the derivatives have to be equal. And then what you find is, okay, so cool thing is, I hate those damn IKs. When you do these problems, those IKs just complicate things. This is a nice problem because they happen to go away. And then I'm going to do my same trick. I'm going to bring the A terms off to one side. And it's kind of obvious what's going to happen is that because the derivative of the B term introduces a minus sign in front, to get them to factor correctly, again, I've got a minus sign in front of the B, and you can imagine what I'm going to get here is I'm going to get A is equal to minus B, which we'll call the anti-symmetric solution, so those cancel. So now I've got A is equal to minus B, okay, and that means, therefore, the wave function is basically sine kx. Okay. So if the wave function is sine kx, now I've got, so there you go. So now I've got a whole other family of solutions. They still has to be, it still has to be 0 at x equals A and minus A. That's still true. Sorry, my handwriting is still awful today. There you go. And of course, that's only true. I just Googled this. I don't remember this stuff, by the way, off the top of my head. But this is true when you have to equal to n pi over 2, and n is equal to 2, 4, 6, dot, dot, dot. Right, because, yeah, sine is 0, at 0, pi, 2 pi, and so I can still call it n pi over 2. It's just that I manipulated my n's to fit the in-between places of the symmetric solution. So this is the asymmetric solution, the anti-symmetric solution. And by calling the interior n pi over 2, I forced my n's to fill in the gaps of what I had before. And yeah, so that's it. So this is the on odd even solutions, symmetric and asymmetric solutions. And in either case, if you do this, what you find is that the energy is h bar squared, pi squared, m squared over 8 ma squared, and on and on and on. Okay, since I'm almost out of time, next time what we're going to do is the finite well, which is going to be way, way more complicated. I meant to do it today, but I just run my mouth way too long. I just want to point out one thing, because I was talking about nanomaterials, and you hear a lot about quantum confinement. Quantum confinement changes the energy of a particle if it becomes smaller and smaller. That's actually right here. Oh, sorry. H psi is equal to eigenvalue, right? I better have an eigenvalue. Here's the energy. you can actually see quantum confinement right here. If A is smaller, the energy goes up. So this is, and then if I do this in 3 dimensions, by the way, it's the exact same thing. As A gets smaller, the energy goes up, and that's actually called the quantum confinement effect that you see in nanomaterials. I also want to point out that this is also the uncertainty principle. You can't know where something is and how fast it's going. Position and momentum don't work together. If you know where something is, you can't know how fast it's going. What's happening is, you should see that since this particle is trapped in a flat potential, all of its energy is kinetic energy. The potential, all the potentials to the left and to the right, but the particle doesn't go there. So all its energy is kinetic energy. So what happens is if the particle becomes more localized, if it's in a smaller box, its kinetic energy rises. And that leads to greater uncertainty and momentum. If you think about it, a car going 1 mile an hour, it's slow, starting, it's going faster and slower, but how much, right? On average, if it's going 1 mile an hour, probably not much. Sometimes it's going 2 miles an hour, sometimes it's stopped, but there's not a wide range. If the car's going 100 miles an hour, I bet you sometimes it's going 130, sometimes it's going 80. There's a wider range. So that's why when you become more certain in position and less certain in momentum, you simultaneously have to have more momentum, which is more kinetic energy. And this is all kinetic energy, so the energy rises. Anyway, other than that, I hope that wasn't a little too circuitous, but I promised you I'd start with self-advising you could get out.